The first thing Neil Armstrong did on the moon, after the ladder and the line everyone knows, was bend down and shovel a bit of dirt into his pocket. That's it. That's the moment. Not a flag, not a speech. A man in a very expensive suit, scraping grey soil into a scoop and stuffing it into a thigh pouch, in case it all went wrong and they had to leave. The contingency sample, they called it. If Eagle had to lift off 10 minutes later with nothing accomplished, at least somebody would have a spoonful of another world to look at. I love that. So unromantic it loops back round to romantic. Anyway, this isn't a video about the landing. Everyone's done the landing. This is about what they carried back up the ladder. The rocks, the dust, the little suitcase of mirrors, and what happened to it afterwards. Which is a much longer story than the mission, because people are still opening bits of it this year and finding things that, going by the physics of 1969, shouldn't be in there at all. Subscribe if you fancy more of these. Right. Let's start on the surface. Here's the thing that surprised me most when I actually went digging into what happened at Tranquility Base. It was a shift, a rushed one. 2 hours, 31 minutes and 40 seconds. That's the whole moonwalk, door to door, from the hatch opening to the hatch sealing again. And in that window, 2 blokes had to plant a flag, take a phone call from the President of the United States, photograph everything, collect an entire geological survey, and set up a small scientific station on ground nobody had ever stood on. There's no version of that which isn't frantic. If you listen to the audio, they're polite about it, but you can hear the clock. The plan for the surface work was something called ESEP, the Early Apollo Scientific Experiments Package. That early is doing a lot of work in that acronym. Later missions carried ULSEP, the full fat version, with generators and drills and geophones and enough kit to keep transmitting for years. Apollo 11 got the trial run. 2 experiments, both designed to be dumped on the ground quickly by exhausted men who had never practiced in real lunar gravity, because nobody could practice in real lunar gravity. There's a photograph of Aldrin doing exactly this, and it's one of my favourite images from the entire programme, though it never gets used for the posters. He's crouched over the seismometer, levelling it, looking for all the world like a man assembling flat-pack furniture in a car park. Back and to the left, sitting in the dust, is the panel of mirrors. Neither of them looks impressive. One of them is still working 57 years later, and we'll get to that. But the rocks were the main event, and the rock collecting was the part most at risk of being cut. They came home with 21.6 kilograms. That's the number that gets quoted, and it sounds modest until you remember it was gathered with hand tools by people whose gloves were pressurized balloons. About 50 rocks, a lot of loose regolith. That's the technical word for the powdery surface layer. And it's a better word than soil, because soil implies something died to make it, and nothing has ever died on the moon. And 2 core tubes hammered into the ground to pull up a little column of material from as deep as 13 centimetres. 13 centimetres. I want to sit on that for a second because it's the sort of detail that makes the whole thing feel human. The best hardware the richest country on Earth could build, the largest engineering project in peacetime history, and the deepest we got into another world on the first go, was about the length of a pencil. The tubes were a nightmare to use, by the way. On Earth, if you want a core sample, you drive a tube into the ground and the ground obligingly compresses and lets you in. Lunar regolith doesn't behave like that. It's been packed down by 4 billion years of micrometeorite impacts with no water and no wind to fluff it up, and by about 10 centimetres down it's dense enough that Armstrong was hammering the tube with the flat of his geology tool and getting almost nowhere. He mentioned it on the loop. He sounded mildly annoyed, in the way pilots sound mildly annoyed when something is going properly wrong. Now, let's talk a little about why the sample was capped where it was, because I think it's the most quietly clever bit of the whole mission plan. The backpacks, the life support systems on their backs, carried roughly 4 hours of oxygen. The moonwalk was budgeted at 2.5. That's not an accident or a scheduling failure. That's a decision somebody made in a room years earlier. We will spend 40% of the consumables on doing nothing because we don't know what's out there. If a suit developed a slow leak, if a backpack ran hot, if one of them fell and couldn't get up, that reserve was the entire plan, and it very nearly got used, in a small way. Both men found moving in 1/6 gravity genuinely disorienting for the first few minutes. The suits wanted to stand up straight. That's what a pressurized bladder does, it tries to become a cylinder. So every step was a small fight against your own trousers. Armstrong worked out fairly quickly that you had to lean forward and sort of lope. Aldrin experimented with a kangaroo hop and reported that it worked fine, but you had to think about it. That's a lovely, very Buzz Aldrin thing to say. Not, it was terrifying. Just, it works. But you have to think about it. Fun fact that always gets me. The reason the flag looks like it's flying is that they threaded a horizontal rod through the top hem, because there's no air to hold a flag out. The reason it looks rippled is that the rod didn't extend all the way and the fabric stayed bunched. They liked how it looked, so they left it. And then, on ascent, the engine blast almost certainly knocked the whole thing flat. Aldrin was looking out of the window and saw it go over. So the most photographed object of the 20th century spent about 6 hours upright and has been lying face down in the dirt ever since. Anyway, back to the collecting. The rocks weren't chosen randomly, but they weren't chosen carefully either, and that's an important distinction that shapes everything that comes later in this video. Armstrong had geology training. Not a lot. A few field trips, a crash course. What he mostly had was a bag, a clock, and a bloke on the radio telling him how many minutes were left. So he did what any sensible person does when the shop's closing. He grabbed a spread. Big ones, small ones, ones that looked different from the ones already in the bag. Toward the end, he was essentially scooping, because the documented sample procedure, photograph it, note its orientation, then lift it, took time nobody had. Geologists back home were, I gather, not thrilled about this. There's a whole genre of polite scientific grumbling in the early literature about the lack of context for the Apollo 11 rocks. Where exactly did this come from? Which way up was it sitting? What was next to it? On Earth, a rock without context is a paperweight, and yet, those hurried, badly documented, semi-random grabs went on to overturn the accepted origin story of the Moon, produce 3 minerals that had never been catalogued anywhere in the universe, and settle an argument in a journal published this year, which suggests that when you've never been anywhere before, almost anything you pick up is going to be interesting. The bar for discovery is on the floor, or in this case, in it. Since we're on the topic of what they carried, it's worth mentioning what they left because the arithmetic mattered enormously. Every gram going up had to be paid for with fuel, so before ascent, they threw out everything they could. The backpacks, the boots, tools, a camera, a bag of unpleasantness I'll let you imagine. There's a famous list, and it's genuinely one of the strangest inventories humans have ever written. Somewhere on Mare Tranquillitatis there is a pile of rubbish with 2 pairs of boots in it. They also left a few things on purpose. A silicon disc with goodwill messages from world leaders etched into it, small enough to sit on your fingernail, medals honouring 2 Soviet cosmonauts who had died, a patch from Apollo 1. That was Aldrin's idea mostly, and he didn't make a fuss about it at the time. He just did it quietly and mentioned it later. I find that a lot with this mission. The bits that were staged for the world are the bits everyone remembers, and the bits that weren't staged at all are the ones that hold up. One more thing about the tools, because I went down a small rabbit hole here and I'm dragging you with me. The geology kit was designed by people who had never seen the ground it would be used on, for hands that couldn't feel anything. A pressurized glove is essentially a stiff balloon with a hand inside it. Closing your fist means fighting the internal pressure of the entire suit every single time. Astronauts came home with bruised, bleeding fingertips and lost fingernails, and that was from the training, never mind the actual job. So every tool had oversized handles, big loop grips, and extensions on the end so you never had to bend down. The scoop and the tongs and the hammer all came with long shafts, because bending at the waist in a pressurized suit is a genuine athletic event and you might not come back up. There's a famous bit of Apollo film, later mission, not this one, of a man on his knees trying to get upright again, and it takes him the better part of a minute. They also had a device called the sample scale, which is exactly what it sounds like, a spring balance for weighing rocks in 1/6 gravity, because there was a hard mass budget for the trip home and somebody had to check. Imagine that as a job. You've travelled 400,000 kilometres, and part of your task list is weighing the shopping, and the boxes themselves, the rock boxes, were milled from single blocks of aluminium and fitted with a knife-edge seal designed to hold vacuum all the way home, so the samples would arrive still surrounded by the Moon's own nothing. Beautiful engineering, it half worked, and we'll come to why. Then the hatch closed. 2 hours, 31 minutes, 40 seconds. and the two of them stood in a cabin roughly the size of a phone box, covered head to foot in a substance no human being had ever encountered, about to find out what it did indoors, which is where we'll pick up. Nobody has ever smelled the moon, not directly. You'd die immediately, and even if you didn't, the smell would be the least of your problems. But something got in. When Eagle repressurized and the two of them cracked their helmets off, there was an odor in the cabin that hadn't been there before. It came off their suits, out of the fabric, out of the seams. Armstrong described it as the scent of wet ashes. Aldrin went with burnt charcoal, or the ashes in a fireplace if you sprinkle a bit of water on them. He also said, in the book, that it was like the air after a firecracker's gone off. And here's what makes this genuinely odd rather than just charming. Every single crew that walked on the moon reported the same thing, independently, in almost the same words. Spent gunpowder. Not gunpowder. Spent gunpowder. The smell after firing, which is a different smell entirely, and they were all quite careful about the distinction. Jack Schmitt, the only actual geologist to go, came in from a moonwalk on Apollo 17 and said it smelled like gunpowder, just like the boys said, Pete Conrad from Apollo 12. Very distinctive smell, never forgot it, never smelled it again. 6 crews, same answer. Now moon dust is chemically nothing like gunpowder. There's no nitrate, no sulfur, no charcoal. There is no chemical reason for those two things to share a smell, and more than 50 years on, nobody has properly explained it. The best guess, and it's a guess from Schmitt himself, who is not a man given to guessing loosely, is that your nose isn't smelling a compound. It's smelling damage. Freshly fired gunpowder and freshly disturbed lunar dust have one thing in common: enormous numbers of broken, unsatisfied chemical bonds, atoms sitting there with nothing to hold hands with. Bring them into a warm, damp, oxygen-rich cabin full of human beings, and they'll grab whatever's going. Possibly including the inside of your nose, which brings me to the single best detail of the entire mission, and one I'd never heard until I went looking. Before they left Earth, a group of people were seriously worried that moon dust might spontaneously combust. The logic wasn't mad if you accept the premise. This is material that has never once, in 4 billion years, met an oxygen molecule. All those hungry broken bonds sitting in vacuum, waiting. Introduce it suddenly to a pressurized cabin full of pure oxygen, warm it up a bit, and you might, some people argued, get smouldering. Possibly fire. The astronomer Thomas Gold at Cornell was the one who first flagged it, and Gold had form for being both right and inconvenient, so people listened. So Armstrong and Aldrin ran an experiment. Not a designed experiment. A vibes experiment. They took the grab sample, put it on the flat cylindrical top of the ascent engine cover, which is essentially the coffee table of the lunar module, and started letting air into the cabin. And then the two of them stood there, in the phone box, on the moon, and watched a bag of dirt to see whether it would catch fire. Aldrin's account of the contingency plan is beautiful in its simplicity. If it started to smoke, they'd stop pressurizing, open the hatch, and chuck it out. Nothing happened. They got on with the checklist. But talking a bit about the dust itself, because the reason it behaves so strangely is genuinely interesting, and it's the same reason it clung to them like a bad reputation. On Earth, sand is roundish. It's been tumbled in rivers, ground against other sand, sanded if you like, for millions of years. Water and wind are polishing machines. The moon has neither. What it has instead is a constant, ceaseless rain of micrometeorites, most of them smaller than a grain of salt, arriving at speeds that make the word fast feel inadequate. Each one hits, melts a tiny puddle of rock, and that puddle refreezes almost instantly into glass, welding whatever fragments are nearby into a jagged little clump. Those clumps are called agglutinates, and they make up an enormous fraction of the lunar surface. They look, under a microscope, like something that would hurt. Splinters and spikes and sharp glassy edges, because nothing has ever come along to knock the edges off. That's your moon dust. Powder made of tiny broken glass. It got everywhere, and I mean that in the most literal, least idiomatic sense available. It clung to the suits so persistently that brushing each other down before climbing back in did approximately nothing. It worked into the fabric, into the wrist rings, into the zips. Some of it was sharp enough to cut the seals on the vacuum bags meant to bring dust home unspoiled, which means several samples were merrily contaminated with cabin air on the flight back, by the very stuff they were trying to protect. There's a joke in there somewhere about a substance that ruins the container designed to keep it pure. Armstrong and Aldrin spent one sleep period on the surface, and they slept, I use the word loosely, they barely slept at all, in their helmets and gloves. Partly for warmth, partly because there was dust hanging in the air of the cabin and neither of them fancied breathing it. Sensible, as it turns out. Schmidt, on the last mission, got a proper reaction to it. Congested, streaming, the lot. Ground control ribbed him about having hay fever sensors, and he came back with the phrase lunar dust hay fever, which is now a real term in the literature. Gene Cernan reckoned it took 3 months for the dust embedded under his fingernails to grow out. And here's the part I keep coming back to, the bit that turns a fun anecdote into something a little sad. There are hundreds of kilograms of lunar material sitting in Houston right now, carefully curated, available to researchers. It doesn't smell of anything. A NASA geologist called Gary Lofgren, who's handled the dusty stuff directly, has said so flatly. Put your nose near it, and there's nothing there. The smell didn't survive the journey. Whatever was reactive about that dust got used up the moment it met air and moisture. The same air and moisture that were coming out of 3 men breathing in a small metal room. Researchers use the word pacified, which is a lovely, faintly ominous piece of vocabulary. The dust was pacified. It arrived on Earth already spent, which means the smell of the moon is a thing that 6 crews experienced, that no scientific instrument ever recorded, that no sample preserved, and that no one on Earth has ever been able to reproduce. It exists entirely in the memory of 12 people, and there are none of them left to ask. I don't know. There's something about that. The most documented expedition in history, filmed and telemetered and transcribed down to the second, and the one thing that actually reached them through the suit was the one thing they couldn't bring back. There's a related detail I'd never clocked, about the stickiness, and it's the sort of thing that only turns up when someone goes back over old footage for fun. An Australian physicist working on his own time decades later noticed that the dust seemed to cling worse on some moonwalks than others, and found it tracked the angle of the sun, which makes sense once you think about it. There's no air on the moon, so nothing to bleed off static charge. Sunlight knocks electrons off the surface, the dust picks up a charge, and a charged jagged grain will happily glue itself to a white nylon suit and stay there. Low sun, different charge, different stickiness. Nobody planned that study. Nobody funded it. A bloke looked at the pictures and counted, and here's the bit that folds back into the rocks. Remember those beautifully machined vacuum boxes? The dust cut some of the seals, so a number of samples that were supposed to arrive still wrapped in lunar vacuum arrived instead full of ordinary cabin air, having been quietly sabotaged in transit by the material inside them. Which is a small thing, and also isn't, because was this contaminated on the way home is a question that has haunted lunar sample analysis ever since. Every time somebody finds something surprising in Apollo material, the first objection out of the gate is, did that come from the moon, or did it come from the inside of a spacecraft full of 3 sweating humans? Half the technical sophistication of modern lunar science is devoted to telling those two apart. Anyway, it isn't purely sentimental, it's a live engineering problem too. Artemis planning has dust handling as a standing line item now. Filtration, seals, the works, because the same reactive surfaces and iron content that may have caused the smell are also what makes the stuff a genuine health hazard if you're going to live in it for months rather than visit for an afternoon. Nobody in 1969 was designing for that. They were designing for 2.5 hours and a lift home, and that's roughly where their heads were when they closed the hatch, still covered in the stuff, and started thinking about the rendezvous. Everything after that is a story about what happened to the cargo, starting with 3 weeks in a locked room, which I promise is funnier than it sounds. I want to describe a scene, and I want you to hold in your head that every part of it is real and was planned in advance by adults. The Pacific Ocean, 3 days after leaving the moon, a charred cone bobbing in 2-meter swells about 900 miles southwest of Hawaii. A Navy diver swims up to it, opens the hatch a crack, throws 3 grey rubber suits inside, and shuts it again. The 3 most famous men alive put the suits on in a space the size of a small car, climb out, and get into a life raft, where the diver scrubs them down with bleach while wiping the hatch with iodine. Then he throws the cloths in the sea and, per the plan, is himself now a biological hazard. Nobody on the aircraft carrier was allowed to breathe the same air as them. So they were winched aboard, walked straight into a converted Airstream caravan bolted to the deck, and the door was shut. That was the greeting. 21 days. The word in the planning documents was back contamination, and it had its own committee, the Interagency Committee on Back Contamination, set up in 1966, which spent 3 years arguing about what to do if Armstrong tracked something alive into the command module. Here's the thing. Nobody involved thought it was likely. Nobody was willing to say it was impossible, and that gap between unlikely and impossible cost $15.8 million. That was the price of the Lunar Receiving Laboratory, built at the Manned Spacecraft Center in Houston across 1966 and 1967, purely to contain a risk everyone privately rated at close to zero. 7,500 square meters, negative air pressure, so anything inside stayed inside. Filters, sterilization chambers on everything going in or out. A 40-room complex for the crew, plus a dozen-odd support staff who volunteered to be locked in with them. Doctors, technicians, a cook, a photographer, and because this is NASA, a public affairs officer. I enjoy that enormously. Whatever happens, however alien the plague, someone must be available for comment. The trailer, meanwhile, sailed to Pearl Harbor with the crew inside, got loaded onto a transport plane with the crew still inside, flew to Houston with the crew still inside, and was driven across the base on a flatbed truck at jogging pace, with the crew, yes, still inside. Then it was docked, the only word for it, to the laboratory via an airtight plastic tunnel, and the three of them walked through into their new home. Each man got a room with a bed, a dresser, a night table, a chair, and a lamp. Next door, an identical room each for their three physicians. There was a lounge, a library, a kitchen, a recreation room. The whole crew section could hold over 100 people if things went very badly indeed, which is one of those design specifications you really don't want to think about too hard. Now, they were not by most accounts delighted. Consider it from their side. You have just done the thing. You are, at that precise moment, more famous than anyone has ever been. Your family is a few miles away. The entire planet is having a party in your honour. And you are in a room, answering debriefing questions through a pane of glass for 3 weeks because of a hypothetical microbe that everyone in the building is quite sure does not exist. Collins found it tolerable. He'd had 10 days of enforced solitude already and seemed almost amused. Armstrong, by all accounts, read a lot. Photographs from inside show them playing cards, flicking through magazines, listening to coverage of themselves on the radio. In the trailer before they got to the better rooms, they were eating microwave meals, which in 1969 was itself a novelty verging on space technology. And then there's the birthday. Neil Armstrong turned 39 on the 5th of August 1969 in quarantine. The kitchen staff at the Lunar Receiving Laboratory baked him a cake. Proper cake, candles, the lot. He blew them out and shared slices with the people who were locked in with him. And in the next room on the other side of a glass partition, his wife had come to celebrate too. So he stood at the glass and mimed passing her a piece through it. I've thought about that image more than I expected to. The most famous man in the world, 16 days after walking on the moon, doing a bit of mime with a slice of cake for his wife through a window. Meanwhile, in the same building, the actual work was going on. The rocks were in quarantine as well. The samples and the command module Columbia, all of it. Scientists behind glove boxes were taking lunar material and introducing it to living things to see what happened. Mice, mostly, but also plants, insects, oysters, shrimp, various bacteria, germination trials, tissue cultures. Even the crew's waste was checked, on the reasoning that if any of them had picked up a passenger, it might be trying to leave. The World Health Organization sent representatives to inspect the lab. 2 independent doctors monitored the whole thing from outside. All extremely serious, all extremely thorough. Nothing showed up. Not in the men, not in the mice, not in the shrimp. After 21 days, a number chosen because it comfortably covered the incubation period for pretty much anything they could think of on Earth, the doors opened and everyone went home. And now for the bit that's aged in a particular way. Historians who've gone back over the planning have reached a fairly uncomfortable conclusion. The quarantine could not have worked. Not was unnecessary, or that we knew, could not have worked structurally from the start. Because think about the splashdown. That capsule came down in the ocean, and the hatch was open to the Pacific air. There was no way around it. The alternative was 3 men suffocating in a sealed can while a helicopter tried to lift them. So the moment the hatch cracked, whatever was inside, including a fair amount of loose lunar dust, because it had come home with them and it went everywhere, was in the atmosphere of planet Earth. Same air, same ocean, same everything. Everything after that point was, in the strictest sense, theatre. Careful, expensive, well-intentioned theatre performed by people who believed in it. One historian's line on it has stuck with me. It looked like a success only because it was never needed, which sounds cynical, and I don't think it should. The Outer Space Treaty of 1967 obliged its signatories to avoid harmful contamination of Earth by extraterrestrial material, and somebody had to be seen to be doing something about that, in a way the public could understand. The quarantine did that. It also, incidentally, gave the sample curators a fully purpose-built facility with negative pressure and clean handling protocols, which turned out to be exactly what you want for keeping rocks pristine for the next half-century. And that part was not theatre at all. That part is still paying out. They kept it up for Apollo 12 and 14 as well, then quietly dropped it. By then the answer was in. The samples showed no organics, no water, no evidence that anything had ever been alive there at any point in the moon's history. There was nothing to catch. Which was, if you think about it, a genuine scientific result. A slightly deflating one. We built a hospital for aliens and the aliens never turned up. 2 footnotes I can't leave out. The first is that the diver, Clancy Hatleberg, is the forgotten man of that whole afternoon. He was the one in the water with the bleach. His job description, if you write it out honestly, was be the one person on Earth permitted to touch the men who might be carrying the plague, and then decontaminate yourself, alone, in the sea, using a bottle. He did it, went into the trailer with them for a bit, got out, and largely vanished from the story. There is no statue of Clancy Hatleberg. The second is what happened to that airstream afterwards, and it says everything about how quickly the mood changed. There were 4 mobile quarantine facilities built. They were used 3 times, then the whole apparatus was declared unnecessary, and the trailers went into storage and eventually into museums. You can go and look at one. It's a caravan. That's the honest visual. The most expensive precaution in the history of the space program was, physically, a silver caravan with the windows blocked. I keep coming back to what that says about how they were thinking. They had no idea. That's the whole content of it. For 3 years, some of the most capable people alive sat in rooms and worked through a problem where the probability was unknowable, and the downside was, in the literal sense, unlimited. And they landed on, build the room, buy the caravan, keep them in it for 3 weeks, and hope we look silly afterwards. They looked silly afterwards. That was the good outcome. It's just very rarely how it feels at the time. Anyway, while everyone was busy checking whether the moon could give you a cold, the mineralogist had put a chip of it under a microscope. So let's talk a little about what they found in there. Right, let's talk about what it actually means to find a new mineral, because I think most people, myself very much included until recently, have the wrong picture in their head. You're not finding a new substance. You're not discovering a new element. Every atom in every rock on the moon is an atom you could buy from a chemical supplier on Earth. Iron, titanium, silicon, oxygen, calcium, a bit of zirconium. Nothing exotic. A mineral is a recipe. It's a specific set of atoms arranged in a specific repeating pattern, formed under specific conditions of heat and pressure and time. Change the conditions and the same atoms make something else entirely. Carbon under one set of rules is graphite, which you can smear on paper. Under another, it's diamond. Same stuff, different instructions. So when I say Apollo 11 came back with 3 minerals that had never been seen on Earth, what I actually mean is more interesting than new rock. It means those rocks were assembled under a set of instructions that our entire planet, over 4.5 billion years and everything from volcanoes to meteor strikes to the crushing depths of the mantle, had apparently never once got round to writing down. 3 of them. From about 22 kilos of hurriedly grabbed rubble. From one flat plain in one afternoon. The first one, and the famous one, is amalcolite. Say it out loud and you'll probably get it. Amalcolite. Armstrong, Aldrin, Collins. Someone at some point decided the 3 of them should have a mineral, and rather than pick one name, they welded all 3 together, and the International Mineralogical Association approved it, and that's now the permanent scientific name of a titanium-rich compound of magnesium, iron and oxygen, formally approved as a species in the early 70s and never revisited. I've decided this is the best possible way to be commemorated. Statues get pulled down, streets get renamed. Nobody's ever going to unname a mineral. As long as anybody anywhere is doing geology, somebody's going to have to write armalcolite in a paper. And, for a fraction of a second, think about 3 men in 1969. Collins never landed, of course. He was in orbit the whole time, going round and round on his own. He's in the mineral anyway. I like that they didn't quibble. The second one is tranquilityite, named for the Sea of Tranquility itself. Iron, zirconium, titanium and silicon, in a formula that looks like someone leant on a keyboard. It's grey to a dark reddish-brown, denser than most things around it, and it forms very late. It's one of the last things to crystallise out of cooling magma, once all the ordinary minerals have taken what they want and what's left over is a sort of chemical scrapings of the pot. The third is pyroxferroite, which is essentially a pyroxene, an extremely common family of rock-forming minerals that has gone wrong in an interesting way. Too much iron, not enough of anything else, and a crystal structure that on Earth would normally be unstable enough to fall apart into something more sensible. Now, the thread running through all three is titanium. The Apollo 11 basalts are strange. They're broadly similar to basalts on Earth, dark, volcanic, the same rock you'd find in Iceland or Hawaii, except that they contain far more titanium than any terrestrial basalt has any business containing, which means the mineral ilmenite and iron titanium oxide is absolutely everywhere in them, not a trace mineral, a main ingredient. Nobody predicted that. There was no reason to expect the Sea of Tranquility to be a titanium mine, and it's not a footnote either. Hold that detail somewhere, because it turns out to be the key to an argument that only got settled this year. We'll come back to it properly at the end. One aside on the naming since we're here, there's a fourth mineral that gets brought into this conversation and shouldn't quite be yoshinite, which was found in Apollo material later, and is named after a mineralogist who'd synthesized something similar in a lab and helped work out where the natural version came from. It's the first new mineral tied to the lunar highlands rather than the dark plains, so it belongs to a different chapter. I mention it because it shows how the naming conventions go. Sometimes you get 3 astronauts welded into a word, and sometimes you get a chemist in Japan who did the groundwork and never went anywhere near a rocket. Both feel right to me, in different ways. So, 3 minerals, 1 afternoon, and a very obvious question. Why the moon and not here? The honest answer, in most cases, is dryness and quiet. Armalcolite in particular is fussy. To make it you need low pressure, very high temperature, and then a fast, brutal quench. The melt has to drop from around 1,000 degrees to ambient quickly, or the armalcolite breaks down into a mix of ilmenite and rutile instead. It doesn't like to be cooled gently. On Earth, magma tends to cool gently, in thick insulating piles, often with water hanging about making everything chemically chatty. On the moon, there's no water, and there's a vacuum sitting directly on top of a lava flow, which is one of the most efficient ways to lose heat ever devised. So the moon isn't cooking with different ingredients, it's cooking with the same ingredients, at high heat, uncovered, and then throwing the pan straight into the freezer. And here I have to slightly walk back the drama. They all turned up on Earth eventually. Armalcolite went first. Within a few years, someone found it in lamprite dikes, at a place called Smoky Butte in Montana, and once people knew what to look for, it started appearing everywhere. The Nördlinger Ries impact crater in Bavaria, kimberlite mines in South Africa, a cinder cone in Mexico, Disco Island in Greenland, spots in Spain, Ukraine, Zimbabwe, a quarry in Texas. Not exactly rare as it turned out, just never noticed. Pyroxferroite followed, which left tranquilityite, the last one standing. For decades, tranquilityite held the title of the only mineral known to humanity that existed on the moon, on Mars perhaps, in meteorites, and nowhere on Earth. That's a properly romantic bit of status for a grey-brown speck to hold. It held it until 2011. Some researchers in Western Australia, Curtin University, spotted it first. Then the University of Western Australia's microscopy people confirmed it by firing an electron beam at the sample and reading the X-rays that came off. Found tranquilityite in the Pilbara, and then in 5 more places, 6 localities, in ordinary dolerite dikes and sills, in rocks that had been sitting in the Australian outback since long before anyone thought to look at them. 42 years, the last lunar mineral, and it was in Australia the entire time. Their explanation for why it took so long is wonderfully mundane. It's rare, it's tiny, and it's prone to changing into something else, so it degrades before anyone catalogues it. It wasn't hiding, it was just small and boring and nobody had a reason to squint. I find this genuinely funny, and also sort of the point. We flew to another world and brought back 3 impossible minerals, and then over the following 4 decades we quietly discovered that all 3 of them had been under our feet the whole time, and we'd simply never looked properly. The moon didn't teach us about the moon there. It taught us what to look for at home. That's a pattern, incidentally, that's going to come up again and again in this video. The Apollo 11 samples are constantly less about the moon than they appear. 2 more bits before we move on, because the mineralogy has some lovely corners. Our malcolite turned out to be structurally identical to a mineral called pseudobrookite, which is common in volcanic settings on Earth. Same architecture, different tenants, so a good chunk of the effort in working out our malcolite's crystal structure went into a question that sounds impossibly nerdy, and genuinely isn't. Which specific seats in the lattice do the magnesium and the iron and the titanium take? Because where the atoms sit tells you how fast it cooled, which tells you what the eruption was like, which tells you something about the inside of the moon. The rock is a thermometer if you can read the seating plan. The second bit is about breccias, which is most of what Apollo 11 came home with alongside the basalt. A breccia is rubble that's been welded into a new rock by the heat of an impact. Broken pieces of older rock, some of them from far away, glued into a lump, which means a single Apollo 11 breccia isn't one rock. It's a bag of rocks from various places and various eras in one convenient package. That's why those pale fragments we're about to get into were in there at all. The astronauts couldn't visit the Highlands. The Highlands came to them, a few grams at a time, delivered by asteroid over the course of 1 billion years, and got baked into the local rubble and sat there waiting. The moon does its own sample return. It's just slow and the postage is violent. There's a whole separate story in the newer sample return missions, the Chinese Chang'e material, particularly the Farside stuff, which is turning up things that don't match the Apollo picture at all. And I've got a video planned about that, because it deserves its own hour rather than a paragraph here. Since we're on the subject of things nobody expected though, let's leave the mineralogy there and talk about how old the rocks turned out to be. Picture the Sea of Tranquility as a place, rather than as a destination. It isn't a sea, obviously, it's a plain, a vast flat dark expanse of ancient lava, dozens of times the size of England, with a scattering of craters and a horizon that's uncomfortably close because the moon is small and curves away from you faster than your brain expects. Grey. Slightly brownish grey in some light. Absolutely still. And here's the bit I can't quite get my head round. Nothing has happened there in 3.5 billion years. Not much. Nothing. No rain has fallen. No wind has blown. No plant has grown, no river has cut, no glacier has scraped, no continent has shoved into another continent. The only events in that entire span have been small rocks arriving from space at high speed, one at a time, over an unimaginable stretch of time, gradually chewing the surface into powder. That's it. That's the whole geological history of the place since before there was anything on Earth more complicated than pond scum. The astronauts stood on a landscape that was already unimaginably old when the first oxygen showed up in Earth's atmosphere. I've tried a few times to find a comparison that works for that, and I don't think there is one. Every analogy you reach for involves something changing. A cathedral weathering, a canyon deepening, a coastline retreating. All of those are processes, and processes need something to drive them, and tranquility has nothing driving anything. It's not slow, it's stopped. The closest I've got is a room in a house where somebody has died and nobody has been in since. Except the dust in that room settled last Tuesday, and this dust settled before the continents did. There's a small consequence of that stillness which I think is genuinely eerie. On Earth, when you look at a landscape, you're looking at the current draft. The hills are being worn down as you watch, at a rate of millimetres per century, and everything you can see is mid-sentence. On the moon, you're looking at a finished thing. The view Armstrong had was, to any meaningful precision, the same view a dinosaur would have had if it had gone. The same view a trilobite would have had. The same one, roughly, that was there before there was anything on this planet you could have had a conversation with. Nothing has been added to that picture in 3.5 billion years except a small pile of American equipment and 2 sets of footprints, and even those are a temporary feature. We know that because of the rocks. And specifically because of radiometric dating, which is one of those techniques that sounds like magic and is actually just very careful bookkeeping. Certain elements decay into other elements at rates that are fixed, known, and stubbornly unaffected by anything. Heat, pressure, chemistry being hurled through space, uranium into lead, rubidium into strontium, potassium into argon. When a mineral crystallizes out of a melt, the clock starts, because at that moment the crystal locks in a certain amount of parent element and no daughter element. Measure the ratio later, and you're reading the receipt. The Apollo 11 basalts came back at about 3.6 billion years old. I want to walk through why that number caused a small crisis, because on the surface it just sounds like a big number, and big numbers stop meaning much after a while. Those basalts came from the mare, the dark plains, and in lunar geology the maria are the young bits. They're the smooth areas, the ones with fewer craters, the ones that were resurfaced by lava after the heavy bombardment had mostly finished. Everyone knew, from crater counting alone, that the dark plains had to be younger than the pale highlands. That much was uncontroversial. So Apollo 11 landed on the young part of the moon. And the young part of the moon turned out to be 3.5 billion years old. Which meant, as the geologist worked through the implications, that even the moon's recent landscape was older than the oldest surviving landscape on Earth. Not older than the oldest rocks. You can find scraps of ancient crust in Canada and Greenland that beat it. Older than any place. There is nowhere on this planet you can stand and look at a view that was there 3.5 billion years ago. It's all been recycled. Every square metre of Earth's surface has been subducted, uplifted, eroded, drowned, buried or ploughed at some point, because we have plate tectonics and weather, and between them they are the most efficient shredding machine in the inner solar system. The moon has neither. So the moon keeps everything. Fun fact along those lines: the footprints. Everyone knows they'll last a long time, and everyone quotes millions of years, and that's roughly right. The micrometeorite rain will erase them eventually, but slowly. What I hadn't appreciated is why they're so crisp in the photographs in the first place. On Earth, a footprint in dry dust would collapse. The grains are round and they roll. Lunar grains are those jagged glassy shards we talked about, so they lock together like a box of broken crockery. You get a print with sharp edges, in dust, with no moisture in it at all. It's a slightly uncanny thing to look at once you know. Anyway, the dating went further than that. Apollo 11 showed the moon had been magmatically active until at least 3.7 billion years ago, and that it had differentiated early, meaning it sorted itself into layers, heavy stuff down, light stuff up, the way a planet does when it's been properly molten. Later samples and lunar meteorites pushed the volcanic record forward to roughly 1 billion years ago, and the Chinese Chang'e 5 material has since produced a beautifully precise date of just over 2 billion for some young basalt, extending the known life of lunar volcanism by the better part of 1 billion years. But that's later. In 1969, the point was that the moon had been alive, geologically, for a very long stretch, and then stopped. Meanwhile, the Highland rocks, the pale stuff, which Apollo 11 only caught in fragments, run past 4.15 billion, and some go to 4.4. That's older than any rock on Earth. Full stop. Those pieces predate essentially everything our planet has managed to hang on to. And then, when enough missions had gone and enough dates had been collected, a pattern showed up that nobody was expecting. A lot of the impact-melted rock from several different landing sites kept giving the same age, about 3.9 billion years. That's the late heavy bombardment. The idea that the inner solar system got hammered, properly hammered, a spike in impacts, not the gentle background rain, for a relatively brief window, long after the planets had formed and settled down. Whether it was a genuine sudden spike, or an artifact of everyone accidentally sampling debris from one enormous impact basin is still argued over, and I mean actively, in current papers, not as a historical footnote. There's a decent case that the Apollo sites all sampled Imbrium, and we've been reading one event as a global era. But if it did happen, it happened here too. Same solar system, bigger target, stronger gravity. Earth would have caught more of it than the moon did, and it would have been arriving right around the time life was getting started or trying to. And we have no record of it. Not a scrap. It's been erased so thoroughly that the only place to read Earth's own bombardment history is on a different world. That's what I mean about these rocks being less about the moon than they look. We went to the moon and came back with a chapter from our own book. There's a comparison I keep reaching for, and it's a bit naff, but I'll use it anyway. It's like how your parents' generation kept everything, every receipt, every photo, every school report in a box in the loft. And your generation has it all on a phone that gets replaced every 3 years, and then one day you want to know what happened in 1997, and the only copy that still exists is in someone else's loft. The moon is the loft. There's one more consequence of all this dating that I think is underrated, and it's the reason planetary scientists put up with the Apollo collection's flaws rather than writing it off: crater counting. It's the only method anybody has for dating a surface you can't visit. The logic is simple. An old surface has had more time to accumulate craters, so more craters means older. Count them, and you get a relative age. This surface is older than that one. Relative is nearly useless on its own, though. You want a number. The Apollo samples gave the numbers. You go to a place, count the craters, then bring back a rock and date it in a lab, and now you have a calibration point. Craters per square kilometre, tied to actual years. Do that at half a dozen sites with different crater densities, and you can draw a curve, and then that curve gets applied to everywhere else. To the rest of the moon, obviously, but also to Mars and Mercury and the moons of Jupiter, with some adjustments for how hard each of them gets hit. Every time you read that some Martian riverbed is 3.5 billion years old, that number ultimately traces back through a chain of assumptions to a rock somebody picked up on the moon and dated in Houston. The whole chronology of the inner solar system hangs off 6 landing sites and a few kilos of rubble. It's a startlingly thin thread when you look at it directly, which is exactly why the Chang'e 5 date mattered so much. It added a new calibration point, in a place Apollo never went, for the first time in half a century. Anyway, now, dates weren't the only thing in the loft. Among all those dark basalt chunks, in the crumbly bits, were a few pale fragments that had no business being there. So let's talk about those next. Before 1969, there were 2 camps, and they properly disliked each other. Camp 1 said the moon was hot, that it had formed molten, or melted shortly after, that it had a layered interior, possibly a small core, and that the dark plains were volcanic, lava, cooled. A small planet essentially that had done planet things and then run out of heat. Camp 2 said the moon was cold, that it had excreted quietly out of debris and never got hot enough to sort itself out, that it was a rubble pile all the way down, and that every feature on its face, including the dark plains, had been made by impacts. Nothing internal, nothing molten, just 4 billion years of getting hit. Both camps were made up of extremely clever people with reasonable arguments, and they had been going at it for decades, because the evidence available to them was photographs of a thing 384,400 kilometres away. You can argue forever about a photograph. That's the entire history of the subject up to that point. Very smart people looking at a small grey circle through a telescope and reasoning very hard. Then somebody handed them the actual rocks, and the argument ended in about a fortnight. The basalt settled it immediately, and settled it for Camp 1. Basalt is lava. There's no ambiguity. You can't make basalt by hitting something with another something. You make it by melting rock in a planet's interior and letting it come up. The dark seas were lava lakes. They had always been lava lakes. The moment the samples came out of the boxes, the cold moon position was over. Fine. Camp 1 wins, everyone goes home. Except that in among the dark basalt and the breccias being rock made of broken bits of older rock welded together by impacts, which is most of what a heavily bombarded surface produces, there were a few small pale fragments, light-coloured. Nothing like the dark stuff around them. They turned out to be anorthosite. Anorthosite is a rock made almost entirely of plagioclase feldspar, which is a calcium-rich mineral that has one interesting property for our purposes. It's light. Not light in colour, though it is. Light in weight. It's less dense than the stuff a magma is usually made of. On Earth, anorthosite exists, but it's rare and it's odd and you don't find much of it. Certainly nobody had a good reason to expect it on the moon, and these fragments were pale, which meant they hadn't come from the dark plane the astronauts were standing on. They'd come from somewhere else, from the highlands, the bright regions, which were a considerable distance away. Something had smashed into the highlands hard enough to throw material across the face of the moon, and it had landed in tranquility, and it had sat there, and Armstrong had scooped it up without knowing. Now, the highlands cover most of the moon. That's the thing to hold on to. The bright stuff is the majority. The dark seas are the exception. So if those pale crumbs were representative, then the bulk of the lunar crust was anorthosite. An enormous volume of a rock type that's rare here, spread across most of another world. Nobody had a mechanism for that. It needed an idea, and the idea it got was properly radical. John Wood, then at the Smithsonian Astrophysical Observatory, published it in 1970. Fast work, given the samples had landed the previous summer. The proposal was this. Early on, the entire moon, or at least a colossal depth of its outer layers, was molten. Not a volcano, not a magma chamber, an ocean of magma, global, hundreds of kilometers deep, the whole surface of the world liquid rock. And as that ocean cooled, it began to crystallize, and the minerals that formed did what minerals do in a melt. They sorted by density. The heavy ones, the iron and magnesium silicates, sank, and the plagioclase, being light, floated, up through hundreds of kilometers of molten rock over an enormous span of time, gathering at the top like scum on a pan, or, and this is the image everyone uses because it's the right one, like icebergs on an ocean. Millions of small plagioclase rafts drifting together, jostling, freezing into a single crust. That crust is the lunar highlands. That's the bright part of the moon you're looking at when you look up. It's the frozen foam of a global ocean of lava, and it's been sitting there for 4.5 billion years, and you can see it from your garden. I genuinely think that's the single most extraordinary sentence in this entire video, and it came from about a dozen pale specks in a bag of dark rubble. The magma ocean stage sits somewhere around 4.3 to 4.5 billion years ago, right at the moon's formation, which is why those highland fragments date so early. They're not just old rock, they're the first rock, the original crust. It never got recycled because there was nothing to recycle it. 2 small footnotes I like. First, the term magma ocean wasn't actually used for a few years after the idea appeared. Wood described the mechanism. The phrase came later, once people had got comfortable with the concept enough to give it a nickname. Second, the anorthosite is often almost purely one mineral. Japanese orbital measurements decades later suggested large stretches of lunar anorthosite are essentially monomineralic, nothing but very high calcium plagioclase, which is exactly what you'd expect from a flotation process. Nothing else was buoyant enough to come up with it. But the bit that makes this the most important result of the mission, more than the minerals, more than the dates, is what happened to the idea afterwards. It escaped. Because once you accept that a body as small as the moon was completely molten at birth, you have to ask the obvious follow-up. What about the bigger ones? A magma ocean isn't caused by anything exotic. It's caused by the sheer violence of assembling a world. The kinetic energy of everything that hits you during accretion, converted straight to heat, plus the heat of a core sorting itself out, plus radioactive decay running hot in a young solar system, all of which apply more strongly the bigger you are. So the magma ocean concept got extended to Mars, to Mercury, to Venus, to Earth, to large asteroids even. Vesta looks like it did the same thing. Planets did not form cold. That's the sentence. That's the whole discovery. Every rocky world in the inner solar system probably began as a ball of liquid rock, and the reason we know that, the reason it went from a wild idea to the standard model taught to every geology undergraduate, is a handful of pale crumbs that a test pilot in a hurry shoveled into a bag on a Sunday afternoon because they looked a bit different from the other rocks. He had no idea. He couldn't have. He was watching the clock. Worth saying, though, it isn't a closed case, and I'd be doing you a disservice if I pretended it was. The rows now are about timing and detail rather than whether it happened. Date the highland anorthosites, and you get a spread, roughly 4.47 down to 4.29 billion years, which is 180 million years of disagreement, and that's a lot of slack for something that's supposed to have been one event. One very carefully dated sample came in at 4.36 billion, which is late enough that some people argue the crust wasn't made by flotation at all, but by ordinary volcanism happening over and over. Another group measured several anorthosites and found they don't sit on a single line, which is what you would expect if they'd formed at genuinely different times. Meanwhile, lunar zircons, tough little crystals that survive almost anything, give ages around 4.51 billion, which is older than the anorthosites and awkward for everybody. So the picture is, yes, there was a magma ocean, yes, Plagiocles floated, and no, we don't precisely agree when it finished crystallizing or how long the whole business took. Somewhere between 60 and 150 million years after the solar system started, probably, before the flotation could begin. I like that it's unresolved. There's a version of science communication where everything arrives finished and polished and you're told what to believe. The reality is a room full of people with slightly different rocks and a strong opinion each, which is more interesting and considerably more human. And that's before you get to the far side, which Chang'e 6 has only just started sampling, and which appears not to match the near side at all. And that's roughly the point where I stop being able to be cynical about any of it. Right, let's talk about the mirror. On a clear night in New Mexico, a telescope points at the moon and fires a pulse of green light at it. The beam leaves the dome, goes up through the atmosphere and spreads. It can't help spreading. That's just what light does over distance, and the distance here is the better part of 400,000 kilometers. By the time it arrives, that tight green pulse is a patch of light a couple of kilometers across, smeared over the Sea of Tranquility. Somewhere in that patch, there's a panel about the size of a briefcase, lying in the dust where Buzz Aldrin put it down. A few photons, and I mean a few, sometimes literally a handful, sometimes one, hit the panel and come straight back. 2.5 seconds after it left, a detector in New Mexico catches them. That's it. That's the experiment. It's been running since 1969, and it is the only investigation from the Apollo program that has never stopped. I find this so much more moving than I expected to. Everything else up there is dead. The seismometers stopped. The generators stopped. The transmitters stopped. The batteries went flat. The electronics froze and cooked and froze again until they gave up. The lunar module descent stage is a corroding metal box. And the one bit that still works, 57 years on, is the bit with no power supply, no electronics, and no moving parts. It's a panel of glass cubes in a frame. Specifically, 100 corner cubes of fused silica, quartz basically, each 3.8 centimeters across, set in a 10 by 10 grid in a panel about 46 centimeters square, recessed slightly into their holes to keep the sunlight off. That's the entire device. No cabling, nothing to switch on. You put it on the ground, you point it roughly at Earth, and you walk away. The clever bit is the shape, and it's the sort of geometry that feels like a trick the first time you meet it. A flat mirror reflects light at the same angle it arrived, which means if it's not aimed at you almost perfectly, your light goes off somewhere else and you never see it again. Aiming a flat mirror at Earth from the moon, and keeping it aimed, forever, with no power, while the ground shifts and the panel settles and the moon wobbles, impossible. A corner cube doesn't care. Take 3 mirrors and join them at right angles, like the inside corner of a room where 2 walls meet the ceiling. Send light in from any angle at all and it bounces off all 3 faces and leaves precisely parallel to the way it came. Not roughly, exactly. The geometry does it automatically. You already own several. That's what's in a bike reflector. It's what's in the red plastic on the back of a car. It's what's in the paint on a road sign, which is full of microscopic glass beads, doing a cruder version of the same job, which is why a sign lights up for the driver and looks dull to a pedestrian on the pavement. The light goes back to whoever sent it. So the Apollo 11 array doesn't need aiming, doesn't need power, and doesn't need looking after. There is nothing in it that can break. It sits there in hard vacuum, swinging through something like 250 degrees of temperature range every lunar day, and returns light. Aldrin set it down and levelled it by eye in a few minutes. He was in a hurry, as we've established. It's been the longest continuously running experiment of the Apollo era ever since. Now, what it's actually for. You fire the laser, you time the round trip. Light travels at a known speed, so time gives you distance. Do it enough, and precisely enough, and you know how far away the moon is to within about 3 centimeters. Modern stations, with better lasers and better clocks, get down to a few millimeters. They're timing the return to trillionths of a second. And from 57 years of that, you get results that have almost nothing to do with the moon. The famous one first. The moon is leaving. It's receding from Earth at about 3.8 centimeters a year, which is a lovely coincidence because it's roughly the width of one of those glass cubes, and also roughly the speed your fingernails grow. Slightly slower than your fingernails, in fact. If you cut your nails tonight, They'd outpace the Moon over the following year by about the width of a pencil. It's tidal. Earth's oceans bulge toward the Moon, but Earth is spinning faster than the Moon orbits, so the bulge runs ahead of it and drags it forward. The Moon gets nudged into a higher orbit. We pay for it by spinning very slightly slower every year. Days are getting longer, not enough to help. Then there's the inside of the Moon. Lunar laser ranging gave the first strong evidence that the Moon has a liquid core. You can tell because a body with a molten center wobbles differently to a solid one, and over decades the wobble shows up in the ranging data. Seismic work later confirmed it. That's a measurement of the deep interior of another world, taken with a torch, and then the big one, which nobody expected in 1969. Lunar laser ranging is now one of the most stringent tests of general relativity anyone has ever run. Because if you can measure the Earth-Moon distance to millimeters, over decades, you can check whether gravity behaves exactly as Einstein said it should, whether the Earth and Moon fall toward the Sun at precisely the same rate despite having different compositions, whether the gravitational constant is drifting, whether there's anything at all hiding in the numbers. So far, no. Einstein keeps winning. But the mirrors are how we keep checking. Oh, and eclipses. The ranging data has pinned the Moon's orbit down so precisely that historians can now reconstruct solar eclipses back to about 1400 BC and know exactly where the shadow fell. Someone wrote down a sky going dark 3,500 years ago, and we can check. Modern practitioners have some wonderfully specific headaches, incidentally. The array is a grid, so at any moment different cubes in it are at slightly different distances from you, which smears the return pulse. They have to model the thermal expansion of the aluminium panel as the lunar day heats it. They have to account for libration, the Moon's slight rocking, which changes which prisms face Earth. The problem stopped being, can we see it, a long time ago, and became, can we model every last centimetre of error? Aldrin's array still works, it's just noisy. The Apollo 15 one is bigger, 300 cubes, and is the workhorse now, which is why there's a new generation going up. NASA's Next Generation Lunar Retroreflector is a single large cube, about 10 centimeters across, designed to sidestep the array averaging problem entirely. The first one landed in Mare Crisium in March 2025, on Firefly Aerospace's Blue Ghost lander, and stations in Europe and the US ranged it successfully. More are queued up on commercial landers heading for the South Pole, which will spread the network geometrically for the first time since 1973. A couple of things I want to flag before we move on, because they get glossed over. First, there are 5 reflectors up there, not 3. Apollo 11, 14 and 15 put down the American ones. The other 2 rode on the Soviet Lunokhod rovers, remote-controlled machines that trundled about the surface in the early 70s, unmanned, and are still sitting wherever they stopped. So the network that keeps testing Einstein is a joint venture between 2 countries that were, at the time, doing everything they could to beat each other. Nobody planned that as a gesture, it's just how it worked out, and it's been quietly true for 50 years. Second, the return is genuinely feeble, and the difficulty is easy to understate. Fire a strong pulse and you might get 1 photon back. 1, out of something in the order of 100,000 million that left the telescope. Everything else is lost to spreading, to the atmosphere, to the arithmetic of shooting at a briefcase from another world, which means the detection problem is less catch the light and more prove that the single particle you caught is yours and not a stray bit of moonlight or a cosmic ray or the detector having a moment. They do it with timing. You know when you fired, so you know almost exactly when a legitimate return should arrive, a window a few billionths of a second wide. Anything outside the window is noise. Anything inside it, statistically over thousands of shots, is the Moon answering. That's the whole thing. Fire, wait 2.5 seconds and see whether 1 particle of light comes home at precisely the right instant. Then do it again, on clear nights, for 57 years, until the pattern in those single photons tells you the Moon is leaving at the speed your fingernails grow. But the old ones will keep working. That's the thing about having nothing that can fail. Long after the new hardware has degraded, that scratched, dusty, half-blind panel of quartz will still be sitting in tranquility, throwing light back at whoever asks. Not everything they left behind was so lucky, mind. The other half of that package lasted 3 weeks. Let's start with the ending, because it's not a triumph, and I think that's more interesting. The Apollo 11 seismometer died, It was switched on the 21st of July 1969, and by late August it had stopped answering. 21 days of data, then nothing. It's the other half of the package Aldrin was crouched over. The seismometer and the mirror side by side, the two experiments that made the cut for the first landing. One of them is still running. The other one lasted 3 weeks. The design of it was actually rather elegant, in a mid-century sort of way. 4 seismometers in one box. 3 long-period instruments arranged at right angles to each other, so between them they could sense ground movement in any direction. Plus 1 short-period vertical sensor for higher frequency stuff. The sharp bangs rather than the slow rolls. Under the lot, a mounting stool to lift it off the ground, and around it a mylar skirt to stop the surface immediately beneath it from tilting as the sun heated it. That skirt tells you a lot about how carefully people had thought this through. Somebody, on Earth, in advance, worked out that lunar ground would warp measurably under sunlight and would ruin the readings if you didn't shade it, and they were right. What they couldn't design around was the power. It ran on solar cells. 2 panels unfolded onto the dust, which is fine until the sun goes down. A lunar night is 14 Earth days long, and it gets to around minus 170 at tranquility. There was a small radioisotope heater to keep the electronics from freezing solid, but no way to generate power in the dark, so the instrument only worked in daylight. Look at the data record and you can see the moon's day written straight through it. Activation on the 21st of July, running until the 3rd of August. That's the end of the first lunar day and the sun goes out. Silence for 2 weeks. Then, on the 19th of August, the sun comes back, and so does the instrument, for about half of a second lunar day, until the 27th, when it went quiet for good and never came back. Best guess is it overheated, which means by one accounting it outlived its design life by about a month. It was never supposed to be a career. Now, the other problem, and this is the one that really did for the science, is where they put it. It was deployed just a few meters from the lunar module. Because of course it was. They were on foot, the clock was running, and they weren't going to march the thing over the horizon. So the most sensitive vibration detector ever placed on another world was sitting next to a spacecraft, with 2 men walking around it, and then a rocket engine. And it heard all of it. Footsteps, the ladder, equipment being jettisoned, the ascent stage lighting up and leaving, which produced enormous signals up around 7 to 8 hertz. And once the humans had gone, it heard the lunar module descent stage itself, metal expanding and contracting as the sun moved across it, creaking and pinging like an old radiator, forever. So the Apollo 11 seismic record is mostly a recording of Apollo 11. For that reason, short life, and drowned in its own noise, the data from it is generally left out of modern analyses of lunar seismicity. It's a footnote. The real seismic story came from the later missions, and I want to be clear about that, because this is a thing that gets muddled constantly. You'll hear it said that the Apollo 11 seismometer revealed that the moon trembles, that there are 4 distinct types of moonquake, that some come from deep inside driven by Earth's gravitational pull, and others come from the crust shrinking as it cools. All of that is true about the moon. None of it came from this instrument. That taxonomy came from ALSEP, the full network, deployed by Apollo 12, 14, 15 and 16, running until 1977 and feeding data back the whole time. 4 stations, spread across the near side, which meant you could triangulate. Over about 8 years, they logged more than 13,000 events. That's where the 4 types come from. That's where the deep moonquakes and the thermal ones and the shallow ones and the meteorite strikes got sorted out. Not from 3 weeks in the summer of 1969. I mention it because I think the tidy version of history, first landing, first seismometer, first great discovery, is worse than what actually happened. What actually happened is that the first attempt mostly failed, and the failure was informative, and they came back with a better plan. Because it did find things in the narrow window it had. It found signals that didn't look like earthquakes at all. On Earth, a quake has a clean structure, a sharp arrival, then distinct waves in a known order, a proper shape you can read. What Tranquility recorded was long, mushy, emergent oscillations. No crisp arrival, no discrete phases, just a swell that built and rang on and faded. Seismically, that shouldn't happen. It implies 2 things that on Earth are mutually exclusive. The material transmits vibration with very low energy loss, so it rings for ages, and it also scatters waves intensely so nothing arrives cleanly. both at once. That's not how rock behaves here. The answer, worked out later, is that the top few hundred meters of the Moon has been so comprehensively shattered by 4 billion years of impacts that it's less a crust than a heap. Vibration entering it bounces around in the rubble like sound in a gravel pit, arriving from everywhere at once, and with no water in the pores to soak up the energy, it takes an age to die away. Hit the Moon and it rings for the better part of an hour. And the other finding, which is quieter but I love it, the natural background noise was very much smaller than on Earth. Our planet hums, constantly. Oceans slapping coastlines, wind-loading trees, traffic, weather, the whole restless business of a living world. There is nowhere on Earth you can put a seismometer and get real silence. Tranquility was silent, so silent that the instrument's own thermal creaking was one of the loudest things around. They'd built a device to listen for the Moon, and mostly discovered the Moon wasn't saying anything. Since we're on the subject of what the network eventually found, there's one result I want to mention because it's the sort of thing that will matter enormously to somebody in about 15 years. The shallow moonquakes. They come from the crust contracting as the Moon slowly cools and shrinks, and the surface has to wrinkle to accommodate it. The same way an apple wrinkles as it dries out. Those are the strong ones. Some of them would be perfectly noticeable if you were standing there, and the ringing means they don't stop after a few seconds the way an earthquake does. They keep going. Minutes of it. There are thermal ones too, driven by nothing more exotic than sunrise. 14 days of night at minus 170. Then the sun comes over the horizon, and the crust starts expanding, and the whole surface creaks and pops, which is a genuine engineering problem for anybody planning to live there. You cannot build a rigid structure on ground that swings through hundreds of degrees twice a month and occasionally wrinkles. Nothing on Earth is designed for that, because nothing on Earth experiences it. Every base concept has to account for it, and the only data anybody has on how often and how hard comes from 4 boxes that stopped transmitting in 1977. There's a lot riding on 8 years of readings from half a century ago, which is a sentence I've now typed about 4 different times in this video, and it hasn't stopped being true. Now, here's my favourite part of this whole section, and it's from 2023. Somebody went back. A researcher pulled the Apollo 11 seismic data, this dead, discarded, contaminated dataset that everyone had agreed to ignore, and went through it by hand. Hour-long segments. 314 hours from the first lunar day, 165 from the second. Just under 500 hours of 1969, listened to 1 hour at a time, more than half a century after the fact. And they built a new catalogue. Sharp onset signals here. Spindle-shaped ones there. The slow rise and fall kind. Some with possible secondary arrivals, spikes and glitches, repetitive stuff that's probably the instrument talking to itself, and a conclusion that there are potentially unidentified events sitting in that data, things that might be shallow moonquakes or thermal ones or deep ones, that nobody ever logged because nobody ever looked. That, to me, is the entire spirit of the Apollo 11 collection in one story. A thing that failed, that got written off, that sat in an archive for 50 years, and it still had something in it, because the person looking had better tools and more patience than the people who first filed it away, which is exactly what happened to the rocks, only on a much bigger scale and about water. In January 1970, 6 months after splashdown, 142 scientists gathered in Houston to say what they'd found in the rocks. The verdict was blunt: no water, no organic matter, no evidence for living organisms at any time in the Moon's history. The samples were consistent with formation at high temperatures, without any subsequent exposure to water at all. Bone dry. That was the phrase, and it stuck for nearly 40 years, and it wasn't a lazy conclusion. It was a good one, and it mattered. Basically, every rock on Earth has water in it. Even rocks that have been fully melted retain some. Hydroxyl locked in the crystal structure, water in tiny inclusions, the stuff is impossible to get rid of because our planet is soaking in it. The Moon rocks didn't have that, which fed straight into the origin story. If the Moon formed from the debris of a giant impact into the young Earth, then the sheer heat of that event would have boiled every volatile off. The water got cooked away. That's why it's dry. Clean, tidy, consistent. The number people used was under 1 part per billion, which isn't "we couldn't find any." It's "we looked hard, and there is essentially none." Right. Well, the problem, and it's the problem underneath most of this video, is that we couldn't detect it, and "it isn't there" are not the same sentence. They only sound the same if you don't say the year out loud. In 2008, a team led by Alberto Sal went back to Apollo material, specifically to volcanic glasses, tiny beads of glass produced when the moon was erupting fire fountains billions of years ago, and found magmatic water in them. Water from inside the moon. Not much, but there. And that was the crack in the dam, because once one group found it, everybody wanted to look, and the tools had improved enormously. The relevant technique is secondary ion mass spectrometry, and the principle is nice and brutal. You fire a beam of ions at your sample, blast atoms off the surface and weigh what comes off. It's destructive, it's fiddly, and crucially it's in situ. You're analysing a specific spot on a specific grain rather than dissolving the whole rock and measuring the average. That matters enormously, because the average of a dry rock with wet inclusions is a dry rock. Between the Apollo era and now, detection limits for that technique improved by 2 orders of magnitude, 100-fold, and when people reran the lunar samples at that sensitivity, the answer came back that parts of the moon's interior hold water at concentrations comparable to mid-ocean ridge basalts. Mid-ocean ridge basalt. That's the rock erupting from the seams on the floor of the Atlantic. That's an ordinary, workaday, somewhat wet terrestrial rock. So the moon went from under 1 part per billion to measured in parts per million. And the bone-dry moon, a result that had underpinned models of planetary formation for 4 decades, was gone. Not because anyone had been sloppy. Because the instruments got better, and the old answer turned out to have been a limitation of the machines wearing the costume of a fact. Brown University's team found hydrogen sitting inside those little glass beads, and that detail is the one that closes the argument. If the water had been delivered later, comets, asteroids, solar wind, whatever, it would be on the outside. Sitting in the beads, trapped when they formed, means it was down there in the mantle when the eruption started. It came from within. It's been part of the moon since the moon was young, and possibly since the moon was made. Which is a bit of a headache for the giant impact story, and people are still working on that. There are papers this year modelling how a proto-lunar disk of vaporised rock might hang onto its water, rather than losing it, because water dissolves very happily into magma, and it turns out you can't cook it off as easily as everyone assumed. Now, since we're on the topic of things in the samples that shouldn't be, let's talk about nitrogen. This one's more obscure, and I think it's better. Lunar rocks are poor in volatile elements. That much has been known since the beginning. But lunar soil is different. The powdery surface layer contains a lot of hydrogen, carbon, nitrogen, and light noble gases that the rocks underneath don't have, which means those elements came from outside. Obvious answer, the solar wind. The sun is continuously firing charged particles in every direction, and with no atmosphere and no meaningful magnetic shield, the moon just gets sandblasted with them. They implant directly into the top layer of dust. Over billions of years that adds up, case closed, except for nitrogen, which refuses to behave. There's too much of it. More than the solar wind can account for. And worse, its isotopes are all over the place. Nitrogen comes in 2 stable flavours, nitrogen-15 and nitrogen-14, and the ratio between them in lunar soil varies far more wildly than any single source could explain. If it were all solar, the ratio should be roughly constant, or at most drift slowly. It doesn't. It jumps about. This has a name which delights me. The lunar nitrogen conundrum. It's been sitting there, unresolved since the Apollo samples came home. People have thrown everything at it. Comets, asteroids, interplanetary dust, cosmic rays smashing atoms apart and producing nitrogen that way. That's real, but the sums don't cover it. Some suggested the sun's own nitrogen ratio had drifted by 50% over billions of years, which is an extraordinary claim to make just to save a model. None of it quite worked. Back in 2005, a group at the University of Tokyo made a suggestion that sounded a bit mad. Some of it came from Earth, from our atmosphere, leaking away into space and landing on the moon. The catch was that they assumed it could only have happened before Earth developed a magnetic field, roughly 3.7 billion years ago. After that, the field would trap everything and shut the tap off. And then, this past December, a study in Nature Communications Earth and Environment turned that upside down. The team, a graduate student called Shubhankar Paramanik, with Eric Blackman and colleagues at Rochester, modelled the whole system properly. What happens to atmospheric ions once they're up above about 250 to 300 kilometres? how the solar wind picks them up, how they mix in a collisionless plasma and accelerate to the same speed and travel along together, where they end up. They ran 2 scenarios, one with fierce solar wind and no terrestrial magnetic field, young Earth, one with weaker wind and a strong field, modern Earth. Modern Earth won, by a distance. Our magnetic field doesn't seal the atmosphere in. It channels the leak. Ions get created up in the high atmosphere, get swept up by the solar wind, and get carried back into the magnetotail, the long streamer of our field trailing away from the sun. And for about 5 days of every orbit, the moon passes through that tail, which is when it collects. They check their model against real Apollo measurements, samples from Apollo 14 and 17, not 11, and that distinction is worth keeping straight. The isotope ratios matched: nitrogen fit, hydrogen fit, helium, neon, and argon fit. So the answer to the conundrum is that we did it. Earth has been quietly feeding its atmosphere to the moon this entire time, and is doing it right now, tonight. The volatile sharing that started when the moon was made never actually stopped. Blackman's line was that it's still going on, over billions of years, and what that means is that the lunar soil is holding a record of our own air, layer by layer, arriving over billions of years, an isotopic diary of Earth's atmosphere, kept somewhere it can't be erased. You know where this is going? It's the loft again. There's a testable prediction sitting in this, which is what makes it proper science rather than a nice story, and I want to spell it out because it's neat. If the extra nitrogen comes from Earth, then it can only land on the side of the moon facing us. The magnetotail only sweeps the near side. The far side never gets a chance. So lunar far side soil should be missing the terrestrial component entirely. Same moon, same solar wind, different nitrogen. Nobody could check that for 50 years, because nobody had far side soil. Then in 2024, the Chinese Chang'e 6 mission landed in the South Pole Aitken Basin and brought some back, the first far side material anybody has ever held. And people have already started comparing the solar wind damage in those grains against Apollo 11, 16 and 17 samples, and finding that the far side grains are more weathered, faster, which is consistent with the near side being partly shielded by our magnetic field, which is the same shielding that makes the whole Earthwind story work. It's early. But there is now, for the first time, a way to check. I'd also gently point out that the whole bone-dry business should make everyone a bit humble, and I include the current lot in that. Because the 1970 conclusion wasn't a mistake. It was the correct reading of the best data available from the best instruments in existence. It was right and then it was wrong, and nothing changed except the machines. Which raises the obvious, slightly uncomfortable question about everything we currently believe. What are we confidently declaring absent right now? Because our detectors bottom out just above where it's hiding. Somebody in 2075 is going to have a lovely time with that. Right. Since we're on the subject of arguments that ran for decades, there's another one worth going through, and it's about magnets. The moon has no magnetic field. Take a compass up there, and it does nothing useful. That's not in dispute, and never has been. The trouble is the rocks. When lava cools, any iron-bearing minerals in it lock in a record of whatever magnetic field they were sitting in at the moment they crystallized. It's a fossil, essentially, a frozen compass needle, and it's a good record. That's how we know Earth's poles have flipped repeatedly, because the seafloor writes it down in stripes. The Apollo samples are magnetized, many of them strongly. Some of them carry signatures suggesting the moon, 3.5 billion years ago, had a magnetic field comparable to Earth's today. In some readings, stronger. That's a problem. A body that size shouldn't be able to do that. To generate a field, you need a dynamo, a core of molten metal, churning, driven by heat, escaping from the middle. Earth manages it because Earth is big, and big things hold their heat and have deep, energetic cores. The moon's core is tiny, a pea in a marble. The physics says a lunar dynamo should have been feeble at best and should have died young, and definitely shouldn't have been producing anything that could outpunch modern Earth. So the field says one thing and the arithmetic says another, and this has been going on since the 70s. The theorist's position was, it's impossible, therefore the rocks are lying, and the magnetism must come from somewhere else. Impacts, probably. Smash something into the moon hard enough and you make a plasma, and plasma does interesting things to magnetic fields, and maybe you magnetize the rocks locally without ever needing a dynamo at all. The rock people's position was, I have the rock, it's magnetized, explain it. Both sides had a point, and neither could win, and it turned into one of those arguments that becomes a permanent feature of a field. A conundrum, if you like. There have been rather a lot of those in this video. Two things have happened recently, and I'll take the smaller one first because it's a nice piece of work. Last year, a group at MIT ran detailed simulations of the impact idea. Their conclusion was that an asteroid-scale collision would throw up a cloud of charged particles that would briefly wrap around the Moon. And if there were already a weak dynamo field there, the plasma could amplify it, temporarily, concentrated on the far side, which is conveniently exactly where the strongest magnetic signatures in the lunar crust actually are. Their framing was the good bit. Rona Oren put it as, for decades it's been, is it impacts or is it dynamo? And the answer might be a little bit of both. And it's testable. The rocks in question are near the far side South Pole, which is precisely where Artemis is heading. And then, in February this year, a group at Oxford published in Nature Geoscience with an answer I rather like. Their answer is that both sides of the argument were right, and the reason nobody could see it is that the sampling was rigged. Not deliberately, by landing sites. Here's the shape of it. Remember the titanium. I flagged it earlier and said we'd come back. The Apollo 11 basalts are absurdly titanium-rich. Ilmenite everywhere, far beyond anything terrestrial. Well, the Oxford team found that titanium-rich rocks and strong magnetic signatures travel together. They're linked. Where you get one, you tend to get the other. Their proposed mechanism is that deep inside the young Moon, at the boundary between the core and the mantle, titanium-rich material occasionally melted. And when it did, two things happened at once. It briefly increased the heat flow coming out of the core, which spun the dynamo up hard, and it produced titanium-rich lava that eventually erupted onto the surface. So the same event that made the strong field also made the rocks that recorded it. They're not two phenomena, they're one phenomenon with two outputs. Now, the crucial part, how long did those episodes last? Not long, no more than 5,000 years, according to Claire Nichols, who led the work. Possibly as short as a few decades. Decades, in 4.5 billion years of lunar history. Those are essentially instants, flashes, moments where the Moon briefly threw a field stronger than anything Earth has ever managed, and then went quiet again for hundreds of millions of years. Which leaves the obvious question, how on earth did Apollo manage to bring back rocks from those exact flashes? The odds should be nil, and this is where it becomes a story about people rather than physics. The mare, the dark plains, are flat. Flat is what you want when you're landing a fragile spidery machine with a novice pilot and a computer with less power than a modern doorbell. So every Apollo landing site was chosen for flatness, or something close to it. The mare are made of basalt, and a great deal of that basalt is titanium-rich. So the Apollo astronauts, by picking the safest places to put a spacecraft down, walked directly onto the rare rock type that records the rare event, and hoovered it up 6 times over, and brought back a collection wildly overrepresenting it. And then, for 50 years, scientists analysed pile after pile of these strongly magnetised titanium-rich basalts, and reasonably concluded that the lunar field was strong for enormous stretches of its history. Nichols's line on it is that the samples are biased toward extremely rare events lasting a few thousand years, and up to now those have been read as representing 500 million years of lunar history. Their models confirmed the bias goes the other way too. If you'd sampled the Moon at random, landed anywhere, grabbed anything, it would be almost impossible to find a rock recording one of those strong field moments. Almost impossible. We didn't land at random. We landed on the flat bits, and the flat bits were the archive of the flashes. So, the Moon's field was weak nearly always, exactly as the theorists insisted, and it was occasionally stronger than Earth's, exactly as the rock people insisted. Everyone was right, and everyone was looking at a different slice of the same history, and the thing that hid it for 50 years was a landing site safety requirement from 1968. I've read that a few times now, and I still enjoy it. It's a mystery solved not by finding new evidence, but by working out why the old evidence was the shape it was, and it needed the old samples to do it. That's what I want to end this section on. Because of the 382 kilograms of material brought back from 6 landing sites, just over 84% by mass is still sitting in the curation facility in Houston. Untouched. Pristine. Never analysed. That was deliberate. Somebody in the 70s looked at the rocks and thought, don't use it all. There will be people later with better machines. Leave them something. They were right, obviously. But the discipline of that is remarkable. You have the thing everyone on Earth wants. You have the career-making sample, and you put most of it in a vault for a generation that hasn't been born yet. The program that finally started opening the special ones is called ANGSA. Around 90 scientists, engineers and curators, most of whom were not alive during Apollo, which I find quietly wonderful. They opened a core tube that had been sealed on the surface of the moon itself and unsealed for the first time in 50 years. They pulled lunar gas out of it, actual gas collected on the moon still in there. They built new tools to do it, because the old ones didn't exist anymore. They processed samples in a glove box at -20 degrees, which had never been done. It had been 30 years since anyone at Houston had opened an Apollo core. They had to relearn how. One of the scientists given access described it as being like a whole new sample return mission, which it more or less is, except it costs almost nothing, and the spacecraft came home in 1969. The curators talk about it as a balancing act, and I think that's the honest description of the job. Use too much and there's nothing left for the people after you. Use too little and you've hoarded a resource that exists to be spent. Ryan Ziegler, who runs the curation office, has put it more or less exactly that way. You don't want to burn the sample, but you do have to get something out of the investment. Imagine having that as your actual daily decision. Somebody writes in wanting a few 100 milligrams of tranquility, and you have to weigh their request against a scientist who hasn't been born. There's a related question hanging over the sealed ones that I find quietly funny. Everyone assumes the vacuum-sealed tubes are the crown jewels, the pristine samples sealed on the moon, untouched. But some of those seals have been sitting there for 50-odd years, and seals are not eternal, and the material inside is the same abrasive stuff that cut through the seals on the flight home. So part of the ANGSA work was building a device to capture whatever gas was in the tube, if any, before opening it, because nobody knew whether there'd be lunar gas in there or just a slow leak's worth of Houston. There was gas. They got it. First time anyone has ever analysed gas collected on the surface of another world. And that particular sample, incidentally, came from Apollo 17 rather than 11, the last landing, not the first, because by then they had drills and time and a geologist, and could take a proper core from a landslide deposit and seal it properly on the spot. The Apollo 11 material is the crude version, grabbed in a hurry, badly documented, contaminated on the way home. It's still producing papers. There's a version of Apollo 11 that ends on the 24th of July 1969, with a splash in the Pacific and a ticker tape parade. It's a good story, and it's the one everyone tells. I think the better one is the boring bit afterwards, somebody signing the rocks into a vault, somebody deciding without much fuss that most of it shouldn't be touched, somebody writing a procedure for storing a tube of dust at -20 degrees for reasons they couldn't articulate beyond a vague sense that it might matter one day. They were writing a letter to people who didn't exist, to be read with instruments that hadn't been invented, about questions nobody had thought to ask yet. And the strange thing is it worked. The dry moon got wet. The nitrogen turned out to be ours. The magnetism argument got settled by a bias nobody had noticed, using rocks collected by a man who was picking things up because the clock was running out. And none of the people who made those decisions got to see it pay off, which is rather the deal. The curator who signed a tube into a vault in 1971 was never going to be in the room when it opened. That's a strange sort of patience to have about your own work. Most of it is still in there. Sealed tubes, frozen samples, a batch that's been sitting in helium since 1971 because someone thought it might be interesting later. Nobody currently knows what those will say. That's rather the point of them. Meanwhile, the mirror's still on the plane, catching a bit of green light every now and then and throwing it back. The flag's face down somewhere nearby. There's a pile of boots, and that contingency sample, the pocket full of dirt Armstrong grabbed first in case they had to leave. That made it home too, and it's been sitting in Houston ever since being asked questions. Nice to think about that. Nothing's finished. Someone's going to open a tube next year, or in 20 years, and find something in it that shouldn't be there, and we'll all have to shuffle the story round again. Sleep well.